All right, it's time. Any questions from the homework? Adam.
Could you go over problem 18 and 22 from 3.4?
Let's look at 18 first. Y equals cotangent 19x to the 14, 16, no, 6. Okay, so for this one, we just apply chain rule. Make sure you see the structure of what's going on here. So I'm writing down all the detailed steps. You don't have to. Number one is the 6. Times the derivative of the inside. Not to do the derivative, separate them. The first one is going to be 1 coming from the x. The second one, I'm going to handle the 14. Times the derivative of the inside, which is x plus cotangent 19. So for there, I'm going to do 1 plus 19 first, times the derivative of the cotangent. That should complete everything. This parenthesis goes with this. And this parenthesis goes with this. Okay, that's number 18. Looks all right? Cool, let's try 22. Oh, this one is playing with the symbols. Let gx we also know that a to the 7th equals 5. F a equals 2. F prime a equals 8. And f prime a to the 8 equals 4. Your job is try to find f a prime and the g prime a. Okay. Play with the symbols. By the chain rule, first you should do f prime, keep x to the a. Times the derivative of the x to the 8, which is this. Okay, so now you just need to put this one in. And go to the resource, a to the 7 is 5. A to the 8, you don't know, but f prime a to the 8 is 4. So 160. That will be the first one. Sounds good? Okay, so it's playing with the symbols. For the second one now, I think it's easy. G prime x is basically fx to the 8 and then prime. Then the first thing you should handle is 8 fx to the 7th times f prime x. Then g prime a is going to be 8 fa to the 7th times f prime a. And f prime a is 8, according to the thing. And fa is 2. So 64, let's see. 2 to the 3, 2 to the 3, so it's 2 to the 13. 2 to the 13 is 2 to the 10. Is this times another 8. That will be the answer. All right. Nick?
3.4, number 25.
Did you say 3.4?
Yeah.
25. Oh. Okay, it's still a matter of order. I would say I will handle sine first, square root second, e to the exponential third, and whatever on the exponents, that will be the fourth. With that in mind, first cosine. Okay. Second, square root. Third, exponential. Fourth, the derivative of this. First, second, third, fourth. Okay, a lot of people are raising their hand. If you have a question about this one I'm doing, just say it. You don't have to raise your hand. Otherwise, I will actually, push you to the in the order you raise your hand. Okay, so if you have one regarding this, just say it right away.
Is it supposed to be cosine plus x to the fourth for the product rule, or is it subtraction?
It's a plus with a negative.
Oh, there. Okay, sorry.
So yeah. So I kind of skipped a step. It's very easy for me to make a mistake, so it's nice for you to point it out. Looks all right. Cool. Now, Austin, what do you have?
3.4, problem 17.
17. Cool. Sine, tangent, pi x. Okay. Yeah, actually, not. It's not bad for you to actually figure out the order before you do anything. I'm going to handle sine first. This 20th root second, sine, tangent, pi in the end. Okay. Once you know that, one thing at a time. Cosine. Okay. Times. Now, 20th root is nothing but something to the 1 over 20th power. So 1 over 20 to the negative 19 over 20 times now the sine times now the tangent, finally the pi x. All right, Aaron.
3.5, number 7.
Are there any more questions regarding the one we're doing right now, 17? All right. 3.5. 7. E to the x over y equals 6x minus 1. So find the y prime is the same as implicit differentiation, so that's for sure. Derivative on both sides. Let's do the easy one first. Okay. On the left, chain rule. Now just do the chain rule. Sorry, quotient rule. Well, it's going to be long. Be patient. Make sure what you're dealing with is correct. So derivative of the top, bottom, minus keep the top, derivative of the bottom. Your job is try to solve y prime. Where's y prime? Here and here. We better move them together. Okay, that's the reason why I want to split this. Times 1 over y minus e to the xy times x over y squared times y prime. So finally I can move this one and this one together. That's going to be y prime minus e to the xy. Let's just e to the x over y y prime equals 6 minus e to the x over y divided by y. Now just divide the whole thing to the other side. This is 1, so Yeah, this looks nicer. So nothing more. Sounds good.
Where did you get the 1 over y from? The first one.
I was trying to split the thing. So technically it's e to the x here times y over y squared. And y over y squared actually cancel to be 1 over y. Come from here. All right. Good, good. Everything else looks okay? Okay, so when you do implicit differentiation, just be patient. Once you finish taking the derivative, okay, your y prime is definitely everywhere. So if you need to split them, just split them to make sure they're isolated. So put all the y prime on one side, everything else on the other side. It's a long process, but it's easy because you're just copying a lot of terms. Okay, so don't panic if you see something messy. It's actually not hard. The more challenging part is actually clear your mind and make sure you know how to take the derivative here. That's going to be harder. All right. Any other questions from the homework? All right. Let's move on. 3.8, exponential growth. Okay. Technically, there is no web work or anything for this section. The reason I want to put it here is number one, you have a project to do later, project 4, which is about this section. So you have to read it. So let's introduce it a little bit. But moreover, I want you to see a little bit about how to do this in real life. When you have derivatives, how do you use derivatives, what we just learned, to solve a real life problem? Okay, how do we reflect to that? That's kind of important because when you go to more and more advanced math class, the math class is so heavy, the math content is so heavy, we don't have much time to actually teach you, like, yeah, how to apply those kind of fancy rules into real life. So once in a while, I will actually do some sections like this to show you how you can use this to do real life stuff. Okay. Meanwhile, if you guys have anything you're interested in, you want to talk about, you saw it's related to calculus, talk to me. Yeah, I can do it in class too. I have pretty rich experiences with working with real life applications of mathematics. Okay. So, exponential growth. What kind of thing grow exponentially according to your experience? Well, population grow exponentially. Half-life, the radioactive decay exponentially. Number 3, compound interest grow exponentially. Right? That's what your teacher taught you. Great. The question is why? Why population grow exponentially other than its effect? That's our concern here. Sounds good? So for this one, we're going to show you why that thing has to be exponential and nothing else. Let's think about a simple setup. Let's take a region. I don't know if you guys can hear it. If you hear some screaming of kids, that's my kid, okay? We're treating him well, so we're not violating any law. Okay, he's just screaming because he's dumb. Okay, here's the region. And we'll assume we have unlimited resource. Now, initially, we have 200 immigrants coming in. They just live there. Okay. Because there is no computation, no any restrictions, so we can roughly assume they have a constant birth rate. It's not realistic. I'm just going to assume it's to be an easy number, okay? 0.2, 20%. And you have a constant death rate, which is 0.1. 10% people die at any moment. Okay. From here, you can see the population definitely grow because the birth rate is bigger than the death rate. It's positive. Now the question becomes, how does the population grow? Some possible candidate, it grow linearly like this. It grow quadratically like this. It grow like this. And we know the answer should be exponentially, right? But let's assume we don't know that. Why does it have to be this case? That's the question here. Okay. With all these assumptions, how can we set up something that we can follow? Well, let's, number one, name some variables. Let's take YT to be the population at time t. We're hoping this one to be an exponential function. Number two, what is y prime t? Changing rate of population at time t. Still okay? Number three, things become interesting. What's the changing rate? Well, technically the changing rate is 0.2, which is the people who are born minus the people who are dead at this moment. Still okay? So what are the people, how many people are born? Number one, it's 0.2. Number two, then if you think about it, it's not 0.2 technically. It really depends on how much population I have right now, right? If I have 100 people, that means 20 people are born right now. If I have 1,000 people, that means 200 people, 200 kids are being born right now. Make sense so far? So the changing should be 0.2 times y, which is my current population. I don't know what it is, but it's y. Similarly, the death rate times my current population. So this gives you 0.1 y. That's not a difficult thing. So we have something like this. The changing rate of the current population equals the people who are born right now minus the people who are dying right now. Plus, the people who are born and die right now is proportional to my current population. A bigger population, more people die, more people being born, a bigger growth rate. Sounds good? All right. That's the equation. Every time you have an equation, you can solve it. Right? So what is this equation? Let's take a look. This equation is something we had before. Y squared minus 3y plus 2 equals 1. We solve it. We have y equals 1 or y equals 2. That's some equation we had before, but this one is different. This one has derivative involved, so we call it a differential equation. That's number one. Number two, if I solve it, my solution is y equals something. From here, you can see y is not a number. Y is technically a function of t. That's what we proposed at the beginning. That's why it has a changing rate. If it's a constant, the changing rate is 0. Still okay? So this is something we call a differential equation, and we can solve. Can we? Well, do you know how to solve this? Do you know any function that if you take the derivative of it, it's basically itself times a constant? Let me say it again. Do you know a function? If you take the derivative, you basically receive itself times a constant. For example, you receive itself times 1, or 2, or 3, or 4. Do you know a function which y prime equals y? What is it? E to the x.
Yeah.
Yeah, thanks. E to the t. Great. Since you mentioned, hold on. E to the t. So this one satisfies y prime equals y. So Julia, What if I add a 0.1 here? Which function?
Would that be like, I don't know, like 0.1 e or something, or e to the 0.1 t or something?
What's the derivative? Let's see. What is it? This, okay? By chain rule times the derivative of this, which is 0.1, which is itself. So you got it. We have the solution. By guessing, we got it. Beautiful. Of course, to continue the initial condition, we actually have 200, but that's not important here. The important part is we have this solution. Why do we have this solution? Because we solved this differential equation. Sounds good? So why does population grow exponentially? Because population satisfies this differential equation. So this differential equation is actually the core. Why something grow exponentially? Sounds good? That also means if you see something new, you see anything new, how do you know if that thing grow exponentially or decay exponentially? You check if they satisfy an equation which looks like this. If it is, exponential. If it's not, no, not exponential. Sounds good? Let's take a look. What does this look like? It's basically y prime equals a constant times y. To summarize in words, anything that with a changing rate proportional to its current size. So let's just say itself. As long as they satisfy this, proportional means times r, it's going to be exponential. If it grows proportionally, it's exponential growth. If it's decay, you have a negative changing rate proportional to itself, it's going to be exponential decay. Sounds good? Population. Well, bacteria. How fast does the bacteria reproduce themselves? It depends on how much population do you have right now. If you have a large herd of bacteria, they grow really fast. If you have a small herd, they grow really slow. But either way, it's roughly proportional to its current size. Therefore, it is exponential growth. Cancer. What do you mean by cancer? Your cell reproduces itself. It doubles itself for a certain time. Okay? For normal people, for healthy people, you have something called a telomere, which stops you from doing exponential splitting. But when you get sick, when you get cancer, that function is lost. Therefore, your cell is going to reproduce like crazy exponentially. Sounds good? So if your stage is early, that means you are still a small size, you have a small growth rate, it's still controllable. But if it's late, you already have a big tumor, okay, a lot of cells. The growth rate is also going to be scary because it's proportional to your current size. Okay. What's the other thing? Compound interest. What's the growth rate of your principal in the bank? What's the growth rate of your loan? What's your growth rate of your credit card debt? Okay. It's proportional to how much you own or how much you owe currently. Make sense here? The changing rate is exactly your interest rate. Okay, so your interest is proportional to your principal, therefore it grows exponentially or it decays exponentially. Sounds good? Student loan, mortgage, they all grow exponentially. Okay. Radioactive decay. We are all familiar with half-life. What do you mean by that? For every 5,000 years, carbon-14 decay by half the content. If you already have 10 pounds, 5,000 years, 5 pounds. If you originally have 1 pound, 5,000 years, 0.5 pounds. Sounds good? We always talk about half life. We never talk about half pound life. That means if you do this much, you lose half pounds. No, it's not fixed. It's half whatever you have right now. Actually, sorry, whatever you have originally. That's why it's called half-life. It's proportional. Sounds good? Some old sayings. If you think about inequalities in the United States, the rich gets richer. It's also in the Bible, right? And poor just get poorer. Okay. How did you get that? Well, rich people, let's assume everybody's capital have a fixed capital gain ratio. Okay, it's like for every $100 capital you have, you gain $1 a year. Who is going to have a faster growth rate? Definitely the richer, because they have a very big Y right now. Therefore, their Y prime is also going to be big. Sounds good? For the poor people, actually, you get poor. Not only you have a small thing now, because your capital is so small, you actually end up in debts. And that debts actually grow on itself with a negative proportion with your interest. Therefore, you get poor. Okay, so next time if you talk about inequality, maybe it makes sense to think about some exponential growth in behind because you have proportional effect. Therefore, by the simple assumption, why does anyone want kid? Therefore, by the simple assumption, you can see like next time when we talk about inequality, right? You're just like, hey, free market, everybody just gain whatever they want, whatever they deserve. Probably it's going to tell you, well, then you're facing something which is like exponential growth, right? The rich gets richer. When you were born poor, you get poorer. When you were born rich, you get richer. So probably there is something the government should be doing, like to reverse this natural phenomena. Otherwise, there's no way. There's no way you can actually keep everybody in the loop. Okay. Another interesting thing you can think about is Pareto distribution. I was talking with the other section. Has anybody heard about this before? Pareto distribution? You can play this game with other people. Let's just say you can do a simple bar chart, talking about 100 people in the room, maybe 20, whatever. And you define a fair game. So nobody take advantage of the system anymore. So it's almost like you can toss a coin, okay? And guess it's head or tail. You have a half chance winning, you have a half chance losing. Number 3, you give everybody a starting fund, $10. Sounds good? Now just say, hey, it's party time. Anybody in this room, just go and find a random person and play that game. Okay, for example, I can find Aaron and just say, hey, let's play tossing a coin. I'm going to guess head or tail. If I win, I got $11. I got $1 from you, and you have $9 left. Sounds good? Okay, it's a purely fair game. Nobody is taking advantage of any other person. Okay. You just play that for a while. At first, you can count how many people have 10. Everybody have $10, so it's 100 people. Okay. After a while, you count again. You have a few people have $10, a few people have $9, a few people have $8, and some people has already lost everything they have to zero. And some people may become rich already. They can be like, I don't know, 200 already. You have $1,000 in total, probably not 200, 120. That looks pretty nice. Sounds good? Okay. Now what happens to the people who hit zero? You just say you cannot play anymore. Unless you want to borrow money from the bank. Let's just say we don't give you the money from the bank. So if you're zero, you're out. Sounds good? Okay. Mathematically, you can prove if you just play this one as t goes to infinity, which means taking the limit, the final distribution will always look like this. Okay. That means the majority of the population will be in no game. They lost everything. Sounds good? Only a few rich people are in the game. Okay, that is called Pareto distribution. Mathematically, you can prove it. Okay, so that's just a natural law. You can play it with a computer simulation or something like that. But keep in mind, Now we're talking about a system. Everybody play a fair game. There's nobody taking advantage of any other person. Sounds good. So it's like the ideal case. Everything these guys earned is by justice. They earned by not cheating, not tricking other people, not taking advantage of other people. They just played purely by chance, half chance. It's not even a big chance like 0.7 against 0.3. Sounds good? But nature tells you, if you do that, you have inequality. Okay, so inequality was not generated according to this model by some people cheating the system. It's just natural. Okay, so now if you're trying to do a political design on fighting inequalities, you should really think about what's the core assumption you want to change here. Okay, probably you shouldn't be attacking the fair game or unfair game. At least that's only part of the reason, because even if you have a fair game, inequality appears. Okay, try to Google this if you're interested. Try to find online some simulators to play with it, and things become, I won't say more fun, but if you let these guys borrow from the bank, that means you can still play with -2 and -3. You just pay a little bit of interest. Let t goes to infinity and see how that thing will end up with. So you will see something crazy. And after that, you know why people actually give you some system called bankruptcy. That means if you hit this, basically don't play anymore. It's gonna be a disaster. You're just going to actually screw your whole life. Okay, there's no one can repay anything anymore. So yeah, that's roughly the case. All right. Other ideas here, clear? It's beautiful, right? Such a simple equation. But somehow it tells you some fundamental principles in nature. And of course, this is not even a good one. In nowhere, no place you will have unlimited resource. That's why we kill each other, right? So let's say this time you have a region. You don't have unlimited resource anymore, which is actually the real case. You have limited resource. More precisely, we don't want to quantify how much water, how much money. We just say, hey, you can only sustain N people, maybe roughly 50,000 or something like that. So we have a maximum capacity. You cannot exceed that. I don't care how you go there. You can go really fast to the capacity and then people kill each other. Maybe you can even go beyond that, okay? And then they fight each other in order to actually sustain. But eventually, as time goes by to infinity, you should have this maximum capacity. No more, no less. Sounds good? How do you change your differential equation? Well, you simply just change it to be something look like this. Your times a term. What does it do? Let's think about it. At first, when y is small, which means y over n is almost 0, right? Then your y prime is roughly this. Exponential growth, you just grow as if there is no limitation because your population is so small. You don't even feel the pressure from nature. Sounds good? As y increase, what's going to happen? Then y over n increase. Then 1 minus 1 over n decrease. Still okay? Then your y prime is going to decrease because originally it's only this term, but now you times something which is decreasing. Then in general, your y prime is decreasing. That means the bigger the population, the smaller the growth rate, or the slower you grow, which is more realistic because you feel the pressure from the environment. Stay okay? What would happen if y is very close to n? That means y over n is very close to 1. That means 1 minus y over n is very close to 0. That means your y prime is very close to 0. That means what? That means as you approach closer and closer and closer to the capacity, you basically stop growing. You don't do that suddenly. You do it gradually. That's a pretty nice model. Not ideal, but it captures something we cannot do before. Now, if you think about what's going to happen before, that's very naive. Exponential growth, that's it. Okay. But after we added this term, say, hey, feel free to grow, but not beyond this. What's going to happen? Well, at first, when your y is small, you grow as if it's exponential. As you get bigger, you grow slower, 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 slower. Still okay? Finally, what happens if you're very close to this horizontal asymptote? You become almost zero because you don't grow anymore, according to the formula we just did. So it will change this graph to something more realistic, like this. Sounds good? That's beautiful. How do you solve this differential equation? Before, how did we solve the other one? We guessed, right? Try guessing this one. It's almost impossible. Sounds good? So how do you solve it? Using everything we learned in calculus about derivatives and later integrations and use some computer software, Wolfram can solve this. Okay. From here, we can see for applications of calculus in real life, you have several people doing different stuff. The first one is you need some people who actually find or define this equation for you. Sounds good? They are called the modelers. They see something in real life, they make some assumptions, they just end up with a differential equation. They give it to you, say, hey, this one makes sense because of everything we just said. It seems like it makes sense. You get some group of people who solve this equation for you. They don't care where it comes from. Sounds good? They just say, well, I see a calculus problem. I solve a calculus problem. Okay. These are mathematicians. Of course, like we said, you can only handle simple functions so far, right? We only have if it's polynomial or trigonometry, yes. What if it's not any of the simple functions? We have no idea how to do it. Sounds good? Mathematician is a little bit better than you, but their ability is limited. We can only handle nice cases. What if the whole thing is not differentiable even? Okay. Therefore, you need computer engineers to solve this one using a computer, which means you compromise, you do an approximation. So, computer engineers. Depending on which major you have, that will be something you want to picture yourself in. If you're computer science, the reason you're learning calculus is probably you will be understanding the problem and solve it using a computer algorithm. You design algorithms. Okay, you analyze how fast that thing is, how big the error is. That's more like a computer science approach. If you're a math major, you probably want to understand this thing from a mathematical point of view. It's a simple function, it's a linear function, it's a nonlinear function. I should solve it using this and this and this math tool. Still okay? But if you are a modeler, you should actually know what this function or this equation is about. You don't even care too much about how to solve it because software can does it, or otherwise I just hire a mathematician to do it. Sounds good? I think most of the person in our class falls into this category. That means you go into biology, you see something there, you say, hey, this is a change in rate problem. I can probably come up with a differential equation describing a biological phenomena, or maybe something in biochem, or maybe something in physics, or maybe something in chemistry. Sounds good? Okay, so talking about application, this is probably most of you guys want to focus on. That is understanding what this function, what this equation is about. Where did it come from? All right. By the way, if you're interested in this, it's called logistic growth. If you're from biology, you will see this sooner or later, or maybe you have already seen it. Sound good? Okay. This is more realistic. Now let's see something even more fun. This models some population, right? Let's say this is the model for population of the fish. Okay, sounds good. Now what we human do is, not only we want fish to grow, we know, for example, Michigan Lake can only sustain this much fish. If they grow exponentially, and eventually they stop growing. You hit the maximum capacity. Sounds good? Okay. Now what human does is, we want to harvest the fish. Still okay? Great. If you harvest the fish, you have a new differential equation. And what the solution looks like really depends on what h you put here. You can harvest at a constant rate, 5,000 fish per day. Sounds good? Or you can harvest in terms of proportion. I only harvest, 10 acre per day. If there are more fish, bigger density, more fish. Smaller density, fewer fish. That's like harvesting with a proportion. Still okay? I can harvest with season. I can only do it in spring and summer. I don't do it during the winter and autumn. That's a sine curve, which is periodic. Still okay? So what do you wonder? You wonder, how can I pick a h to achieve the following? Number one, I pick h such that I don't break the system. Because if I do too much, the whole system, the trajectory originally was like this. If you do too much, it go like this. And the fish just dies out. Okay, so pick fish without breaking the system. No extinction. Meanwhile, maximize my profit. The more you fish, you're risking that you may break the whole thing. But of course, you want to do more because you make more money. Sounds good? That balance is actually how people design. Like every time you have some ruler and just say, hey, anything shorter than that, you just throw them back to the lake because our model tell you so. Sounds good? Think again. Think again. What if this is not the population of the fish? It's the population of the cancer cell. This time you want to do some drug. This drug kills some cancer cell at any moment. You can do it periodically. You can do it proportionally. You can do it a fixed amount of number. And you can even do a surgery to remove the whole thing. Sounds good? But this time, you're actually looking for the opposite. You don't care about maximizing anything. You care about, can I destroy the system so the whole thing stopped exponential growth. I want the thing to die out this time. Still okay? Cool. So once you have differential equation, you can actually start to put something on your own. Then this thing is called control problem. And this thing you put in is called control. That's where human comes into play. In real life, this is going to be hard because the differential equation is going to look hard. You have a lot of uncertainties. You cannot observe things as they are. Maybe you have 1,000 variables. You can only observe 3. Still okay? You have live feedback systems. Okay. More or less. For most of you guys, if you're going into engineering, this is where you will spend most of your time on. For example, SpaceX. They have rockets, right? You can easily write down a differential equation the rocket satisfies. It's free fall. Make sense here? Okay. But what do you want to do? You want to use some human intervention to change the free fall, to make sure that the head always stay up, the tail always stay bottom, so they can land. To make sure that if there's air resistance, how you respond to the air resistance or the wind or anything. Make sense so far? So basically, you are manually inputting a function here. You don't even know what that function is. You need to design that in order to change the original free fall of the rocket into something slow, to make sure that it's always heads up, to make sure that it always lands at a certain place. So that's actually a big, complex control problem. But if you go there, you will find you're doing nothing but solving differential equations, or more precisely, solving control problems. Sounds good? Okay, biology, physics, engineering, you will see this a lot. We don't offer this class in UWL. So try to learn by your own. You can actually already start. It's not too hard. That's the first thing about differential equations. It's pretty nice, isn't it? Let's try another example. Harmonic oscillator. Which is the spring mass system. I think everybody has seen this before in your elementary science class. You have a wall. You have a spring attached to it, which is pretty stable. Don't fall off. And you have a relaxed state, which means if you just let the spring naturally extend, you put this object there, this one just stay there forever. Now what we do is, of course, we take this spring, we stretch it. Okay. So what's going to happen? Well, we receive a big tension from the spring, which wants to pull the object back. But because we're holding it, it stays here. Sounds good? Of course. Now what's going to happen if you just let it go? What's going to happen? This thing shake, and 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 shake around the relaxation point. Make sense so far? When they actually reach the relaxation point, they don't have force anymore, but they still have a velocity, so they still have to go a little bit further. And then the spring starts to push it back. Okay? And the back and forth, back and forth, and back and forth. So if you think about it, this one shakes. And if we assume there is no friction, this one basically shakes like a sine wave. Or does it? Is this something just looks similar to a wave, but actually it's not sine? Or if it's a sine wave, why? Like the thing we said before, if the population grows exponentially, yeah, we know, but why? Sounds good? With differential equations, we can actually answer that question. We can tell you firmly why this one has to be a sine. It's not something similar to sine, okay? Because you can have some wave look like this, which is clearly not sine, but you may mistake it to be a sine. It's just a wave, back and forth, right? Why does it have to be sine? That's the question. All right. Let's continue tomorrow. I need to redraw the whole thing. Let me redraw the whole thing. So let's continue next time. That's all for today. There's no web work for this section, just for fun. So don't look for any.